So please have a seat, and we are ready to start. So I'm Franck Carré. I'm with the French Commission for Atomic and Alternative Energies, and I'm a chief scientist of the Nuclear Energy Division. I'll be very pleased to, let's say, co-chair this session with Mr. Roger Garbil, whom everybody knows because he's one of the main organizers of this very successful conference. As you know, he's a project and policy officer in the Euratom Research Unit of the Directorate General for Research of Innovation at the European Commission in Brussels, Belgium. And also, we will work with Ms. Theodora Rettegan as a rapporteur, and she's an associate professor from the Chalmers University, and her field of expertise is chemistry and chemical engineering, nuclear chemistry, and industrial materials for recycling. Just a few remarks just as an introduction to this session on advanced nuclear systems and fuel cycle. So let's say over the past months, there have been signs of increasing awareness that nuclear should be part of the low carbon energy sources to really achieve carbon neutrality by 2050. And I just take three examples. European Commission had a communication in late November that stated that together with, let's say, renewable energies, 15% of nuclear power would be the backbone of a carbon-free European power system. So this is one statement. Another interesting statement is in the International Energy Agency, a special report that was presented last week at the 10th Clean Energy Ministerial in Vancouver, and that stated that nuclear power in a clean energy system, and this is the title of the report, Nuclear Power in a Clean Energy System. And really this was a communication that the nuclear was really among the, let's say, low carbon energy sources to really fit within the 2 degrees or 1.5 degrees. The third and last example is, let's say, a statement by the Union of Concerned Scientists in the United States in a report that was published in November 2018 that says, so the sad reality of serious climatic changes dictates that we keep an open mind about all of the tools in the emission reduction toolbox, even ones, and in parentheses such as nuclear, that are not our personal favorites. So I think those are signs of increasing awareness that really nuclear should really team with renewable energies towards a carbon neutral energy future. But for the nuclear to really be a strong part of the energy mix in 2050, there are a number of conditions to be met. So improving cost effectiveness and flexibility, enabling high levels of safety at lower cost, assuring a sustainable long-term fuel cycle, resolving nuclear waste and environmental issues. And then improving nuclear along these lines calls for innovation and fosters research for new technology, new designs, new reactor types, which is the precise theme of this session. So this makes the current period and the years to come quite interesting because innovation really is required and there are signs of emerging innovation. So it makes the coming period very interesting and also decisive for the future of nuclear power and possible extensions to other energy products such as heat and hydrogen. So within this context, we have an exciting session on advanced nuclear systems that will well reflect the current spirit of innovation with, let's say, a wide variety of nuclear systems and the presentation of a wide variety of innovation in key topics. And we will start with the keynote presentation by Dr. Noel Camarca. So Dr. Camarca is the Director for Research and Development and International Affairs at the EDF, our utility EDF in France. And prior to joining EDF in 2007, Dr. Camarca had a distinguished career at CEA, where he had several key positions, including that of Director of the Fuel Cycle Divisions at the end of the 90s. So please, Noel, please, the title of your address will be SNETP, SNE, and ERA, GPNM, Research and Innovation.
Thank you, Frank. You know me far too well. I am only a reasonable special advisor for nuclear R&D at EDF Engineering, a new nuclear project. And I speak to you as SNE Chairman, European Sustainable Industrial Initiative, using Generation 4 demonstration fast reactors and their relationships with the material science community the ERA JPNM, Joint Program on Nuclear Materials. The projects of JPNM will be detailed in the session by Lorenzo Malebra from CIEMAT, who is in the front rows, and they will be detailed later in the session. So who are we? We are a task force, and we work under Memorandum of Understanding under the SNETP platform. We were founded in 2010. We were 13 founders at the very beginning. We are now 31 members. And latest comer is Paul Scherrer Institute from Switzerland, who joined in 2017. From industry, we gather 12 members. From research organization, mostly funded on government money, we gather 19 organizations. And as is classical in the SNETP platform, we have a two-level structure. Basically, SNE is an instrument for coordinating the implementation of the platform pillar on sustainability of nuclear fission based on generation 4 fast reactors with a closed fuel cycle. 3 main technologies are studied in Europe with the objective to reach the demonstration stage. It is an ambitious goal, beyond €1 billion minimum. It's a minimum. We have the following technologies: lead bismuth and pure lead, sodium fast reactors, and gas fast reactors. Now, in the past 10 years, the maturity of our projects and systems have evolved. Between 2010 and 2018, sodium fast reactors were the leading technology and demonstration project in Europe. Remember, I'm speaking only for Europe. The world situation is quite different. In early 2019, there was an announcement by the French government that sodium demonstration projects are no longer needed for the short and medium term, as industrial perspectives for sodium reactors are postponed. And the new French strategy for closing the fuel cycle has been detailed by a high-level government officer, who is Philippe Storr, from CA Director for Nuclear Issues, and he gave this formal presentation at a recent conference in May 2019. So since I'm no longer a government officer, I will duplicate some of his official presentation. So now the MIRA demonstrator, SCKCN, is now the leading Generation 4 project in Europe. It uses lead bismuth as a coolant, and it will be Hamid, also in the front row, who will be saying most of the things concerning MIRA. And now the 2 other technologies, pure lead, sodium and gas technologies are also studied in Europe. We had a lively debate at the seminar this morning. What can be said is that the demonstrator stage is not yet as advanced as the stage of MIRA. Okay, so this is MIRA. Remember, it is a multi-purpose flexible irradiation facility. It's an accelerator-driven system using a 600 MeV proton LINAC and a spallation target source and a cooled reactor with the lead bismuth, which can operate in the 2 modes. It is a multi-purpose flexible irradiation facility, serve the category of research reactors. We now go to lead technology, pure lead, and we had a very good presentation of its objectives by Senator Valeka, Romanian Senator Valeka, this morning. So it, in a way, has a variety of objectives. It is both a demonstrator devoted to the development of lead fast reactor technology. It can also be a reactor addressing the concerns of safety and sustainability of nuclear energy. And it is also a research infrastructure to build and maintain the European leadership on scientific excellence. I have quoted here power range. The power range of Alfred would be of the order of 120 megawatt electrical, which qualified such a project in the category of small modular reactor. In order to get the modular objective, you have to take a look in a more detailed way at the design. Remember that power is not enough. Next, the Falcon project. supplemented, we heard this morning, by a national Romanian project, the Jesina National Project. So originally the Falcon project was founded in the around 2013 or 2014, just before 2014. It joined Ansaldo Nucleare, Enea from Italy, and our host in Romania, which is ICN Ratten. It is useful both at the EU level, at the national level, and of course at the local level. And the Mioveni nuclear platform in this very country is the candidate site for Alfred. If you are optimistic, if money can be raised, but we have heard some good news this morning, then construction can be envisioned in the 2030 range. And the collaborative effort around Alfred is very original, typical of Romania. It is a research infrastructure covering many scientific objectives. And again, at the specialized seminar this morning, at the session, we heard a very good presentation from Dr. Tarantino from Enea on pumps, big components, steam generators, fuels, and also innovative concepts. For instance, in fuel, you have understood I am a fuel engineer by training, they want to use grids, not hexagons. The EU has given a great amount of support to the Alfred project. So this slide was already presented this morning. So you can see R&D indirect and R&D direct actions. You can see of the order of 90 million euros. Of course, this is over a 10 to 15 years period, many projects. And in the memberships, associated members and partners can provide what is called in-kind contribution. Now we now come to the, also Romanian support should be always mentioned. You can see on this slide, past initiatives are all of the order of 50 million euros. Short-term availability is anywhere between 2 and 20 million euros. And there are good plans in the future and for the facilities mostly, which I've seen this morning, with the use of European structural funds, up to 45 million euros to support the research facilities for the components. I now go to the second European fast reactor technology, which is the gas fast reactor technology. It originates from a design going back to 2000-2005 on the left-hand side, the Allegro design of 75 megawatt thermal. And there was in the 2000, so that's nearly 20 years ago, a plan to make a jump between such a design and a FISA 2400 megawatt thermal reactor. The technology in itself has a few tricky parts. You must have a reactor vessel. You must have, of course, main heat exchangers. You must have decay heat removal systems, because in gas systems, if you have a leak, then you lose the pressure and the coolant at extremely rapid rate. And you have to have what is called a guard containment vessel, enclosing the reactor vessel itself and the loops in order to provide backup pressure in case of lockout. And it has taken the Central Europe team quite a number of years in the SNE structure, but also nationally, to gather expertise, knowledge, and to be able to reach that point of the order of a good conceptual design. Now they announced a new strategy that's early 2015, so that's already 4 years ago. The partners V4, G4 are from Central Europe, Czech Republic, Slovakia, Hungary, Poland, with the French CA being an associate member. So the idea was to start building, if possible, rapidly. Rapidly can mean over 10 years from time to time. So reduce the power from 75 megawatt thermal, optimize the core configuration, gather a team between 4 countries to be able to do a conceptual design, which is not very easy. It takes some time. It is easy, but you have to discuss, negotiate, take time. And 2 major technical decisions. concerning the management of loss of coolant accidents and station blackouts, and the other one concerning concerning fuel, so uranium pellets, enriched uranium pellets, MOX maybe, but mostly enriched uranium in stainless steel. So you build the first machine and then you qualify the true material, the true fuel, which is a ceramic fuel. So here is an example of the calculation performed by the Slovakian team, Vuje. You can see on the left-hand side a core going up to 75 megawatt thermal. On the right-hand side, a reduced core going up to 37.5 megawatt thermal. And I have recalled at the bottom, with the help of the Allegro people, the outlet temperatures. If you have a classical core, you can go to 560 degrees C. If you go to ceramic with a carbide and silicon carbide, then you can go to much higher temperature and reach 850 degrees C. Now we go to some news from France. We had Mike, as you have understood, I am a French gentleman. So there was indeed a major evolution in 2018, announced in early 2019. So yes, France wants to keep the closure of the fuel cycle, but generation 4 reactors will be pushed back in the long-term future. So in the short term, we have an industry and we have plans to run, so we will introduce MOX fuel to the 1300 megawatt PWR reactor fleet. This is a big fleet. We have up to 1300 megawatt machines. Not all of them will be on MOX fuel, but this is already a big industrial effort. In the medium term, the government is requesting that we investigate the multi-recycling in PWRs using what is called now MOX2 fuels. So we have, you have to, well, I will not go into the details, so you should call them second generation MOX fuels, so new fuel assemblies. You can use enriched uranium rods, so Corail and mix assemblies, and you try to find the limit multi-recycling in thermal reactors. And long-term still remains generation 4 reactors and full closure with the sodium reactors and corresponding cycle plants. So again, you can see that we have an R&D program going on between French CEA and industrial partners, EDF, Framatome and Orano company. The main effort which is now starting and going up to speed is study the potential industrial deployment of multi-recycling in pressurized water reactor. You do that both through scenario studies and you do that also with what would an experiment look like. And so the idea is to go from mono-recycling or single recycling to complete fast reactor recycling of plutonium, but fast reactors are pushed back to the end of the 21st century. And you have a number of scientific challenges to be addressed, which I will not detail. I'm a bit short on time. We are also thinking about small modular reactors. Maybe most important, we are now reaching 10 years beyond the creation of the ESNI organization, so it is time to reflect about what we have been able to do. So one, we do promote main projects and technologies. We always think in Europe of projects and technologies, which is not the same as a technology by itself or a project by itself. Maybe I'll get a question. But we do not distribute money. So what do? We evaluate project and systems maturity. As you've seen, it can change. In the course of 10 years, a technology and a project can be moving very fast, and the one can be slow. You take a look, 7 years later, it has changed. It has happened between ASRID and MIRA, to be very frank. We do coordinate research and European research teams, because there are very good European research teams, and they should be helped, encouraged, get advice in their efforts. We try to give technical advice to emerging projects, whatever they are, The emerging projects of the future will not be the emerging projects of 2010, 2011, 2012. In the technical field, and we had a debate this morning already, we have achieved some harmonization of fast reactor fuel for R&D. I'm speaking only for R&D in Europe, and mostly fast spectrum. When you take a look at other generation 4 fora in the world, the communities are much more diverse. In Asia, you can find 3 fuels. You can find carbide in India, you can find metallic in India and Korea, and you can find oxide, for instance, in Japan. In Russia, which is an enormous, big industrial player in fast sodium reactors, you also have 3 types of fuel. You have pelletized MOX, you have what they call vibropacked MOX, and they have strong research on nitrates. Of course, Generation 4 International Forum, GIF, worldwide, is powerful enough to treat all kinds of fuels. We are a small pillar in a platform in Europe, so we try to specialize. Now, for the next 20-25 years, Euro 3 ESNI will use one R&D fuel for the leading projects, for the demonstrator projects. Of course, there can be other basic research. I will maybe tackle that with the moderator. So the idea is to promote mixed uranium and plutonium oxide, pelletized MOX. We have no other thing in Western Europe. And there will be a small offshoot for the Allegro program. Phase 1, phase 2, they will probably be using uranium, enriched uranium oxide. We believe that such a choice must be consolidated in a detailed research program in the future for the next 10 years. For the 2019-2023 Euratom R&D program, MOX fuel research is funded through the INSPIRE and ESFR SMART project with European Commission money and also with member states' money. We are very grateful to the Commission to provide such a support, even though it is modest or medium amounts of money. They maintain very good research team, and on this research team, you can foster new ideas for larger scale projects, and this is what we do with the industrial French partners. We are also funding fast spectrum MOX at a higher level, a few times higher than what the Commission money is able to do. We need to increase knowledge on second generation plutonium which is coming from MOX, from PWR fuel, and we want to maintain industrial capability in France, which will be useful for all the other projects. If MIRA has to start the fuel off on its own, it's another €1 billion that you have to find. If you can reuse already existing industrial facilities, then it is much easier. I make the same offer to Alfred. Please do stay to MOX fuel, but you can go to other fuel in basic research. But if you have to build a huge, big facility for several tons in nitrites, my God, you have another big tag of beyond €1 billion. Coming back to the technology projects, MIRA has moved ahead significantly, is now the first European fast spectrum demonstrator project in the ESNI community. And let me recall that if the French government has made decision for its own country, sodium is technology worldwide, is becoming industrial. I am very glad to recall the production by BN 800 Russia, 5.6 terawatt hour. So this is indeed no longer research. This is an industrial reactor heating and providing electricity to a whole region, to a whole oblast, Yekaterinburg. So large power reactors will remain the mainstream of this technology, but other ideas can emerge in Europe, and there will be small modular reactors using the sodium technology. Teams are gathering, and so we will reuse the work of the previous European projects. Allegro and Alfred are particular since they have access to European Structural Fund. I was very glad of the seminar this morning. 22 million euros of Romanian Structural Fund are in the pipe. They will be very well used for research facilities in Mioveni. So congratulations. I hope you do get this Structural Funds budget, and then you can move on with the project. I was glad to see an upper end figure, up to 100 million euros. Congratulations again. Please do succeed. And the 4 projects, whatever the technologies, will need public support and acceptance from the R&D community at large. They will need long-term research in parallel with project basic and detailed design. As everybody in the room knows, construction will depend on the funding, so good luck to everybody who is looking for fund. Thank you.
Thank you, Noel, for having chaired for so many years ESNI, and also for this quite informative overview of the program. Are there questions to Mr. Kamaka? Please.
Yes, Janne Wallenius from KDH. Yes, it's quite clear that the focus in Europe is on MOX fuel. There is also a country that we don't know if it is in Europe or not, the United Kingdom. And the government in the UK granted feasibility study money for 8 different companies to develop advanced modular reactors. And here it's quite interesting to note that not one single of those concepts actually would apply MOX fuels. They would operate on trisofuels or uranium oxide or uranium nitride fuels, and enriched as such. But what is your comment on that?
How many are fast spectrum? If they are light water reactor...
Four fast spectrum reactors.
Okay, so in that case, they have to develop their fuel, so it's another few billion euros on the table.
Well, the UK government has made the assessment that that is more feasible than MOX fuel nowadays. So.
Okay, we'll see, we'll see. Again, I repeat, any project saying I'm going to run on MOX fuel has capability and has a lower price tag, and they are always already all looking for money. This is only one part. Then you have technical difficulties. If you go to very high temperature sintering with not so good quality plutonium, then you are running into difficulties. But we'll see.
Other question to Mr. Kamaka. Take a chance because Mr. Kamaka has a harsh time constraint, so he will have to leave soon, so please ask questions. I have a difficult question for you.
We have known each other for 27 years.
Well, you said that, in fact, ESNI was born or launched 10 years ago. And then and you've been chairing ESNI for a long time. So what are your vision of priority research and outcome for, let's say, ESNI in the maybe 10 coming years is too short, maybe in the 20 coming years. So both in terms priority in terms of research and possible outcome in terms of technology demonstrator.
I believe we should continue with our original charter. So somebody has to promote demonstrators in Europe. It is a difficult task. It would be much easier to go to smaller projects and say, okay, let's take the fashion and say, okay, there is a new fashion, let's pick it up. We stay true to our charters, so I believe for the next 15 years, Myria will be the leading project in Europe, and I wish extremely good luck to Alfred and Pure Lead Technology. They have a right to succeed. There will be other smaller technologies. Janus has mentioned it, and we will see how they fare. Well, that's a basic belief. So continue to promote demonstrators. Do not let it, the very limited amounts of money we can gather starts going into a few small rivers.
Thank you, Noel. Any last question for Mr. Kamaka? Conchetta. Conchetta Facio.
Another difficult question. Yeah, thank you for your nice presentation. My question is as well difficult. So we are observing a certain trend worldwide on molten salt reactors, with also some announcement to build prototypes. So what is the perspective inside the ESNI looking also on this type of reactors? I mean, enlarging a little bit with respect to the four systems there.
Again, our individual members, some of them go and join as molten salt reactors project. Well, you say very good. If one molten salt reactor emerges with enough support from member state governments, then he's eligible to our charter and he can join us. And I had discussions with the Netherlands government in a set plan conference, that was during the terrible days in Brussels for all who remember 2015, 2016, when they had this attack. And I told the Netherlands government, please, you are a member state, if you want to fund a big team, why not? But what we cannot do is have a few university professors with 3 PhD students and say, we want to join ESNI on molten salt reactors. I think it is not our spirit. Try to reach either the demonstrator stage or the conceptual design for a demonstrator. But in molten salt reactor, this is far away.
Thank you, Noël. Let us thank Mr. Kamarka again. So, then let us have the second address. Well, the speaker for the next address will be Dr. Konstantin Mitikyuk. And Dr. Mitikyuk is a leader of Advanced Nuclear Systems Group at PSI, the Paul-Scherrer Institute, since 1992. He's expert in fast neutron reactor safety. In fact, he was expert. He developed first his expertise at the Kurchatov Institute before joining Paul-Scherrer, continuing, I mean, in the same field of expertise. So he has been the coordinator of a number of projects dealing with the safety of fast neutron reactors in Horizon 2020, as well as projects dealing with research tools, let's say, concerning, let's say, safety of fast neutron reactors. And then Dr. Mitikyuk will address the following subject: research and development in support to safety assessment, design, and licensing of ESNI Gen 4 systems.
Thank you very much, Dr. Kare. So, we have difficult tasks, so I would like to present you 9 projects during the next 20 minutes. So, this presentation, this paper is teamwork. So I have a number of co-authors. It's Luca Mirabili, Massimo Forni, Jacek Igilski, Nathalie Giraud, Akas Horvath, Jean-Lynn Klosterman, Mariana Tarantino, and Alfredo Vasili. So I am speaking on their behalf. So I start as introduction, a kind of repetition, what was already presented by Professor Kamarkat before, just to show you these nice pictures of the different reactor systems which I'm going to speak about. And to remind you again that European Sustainable Nuclear Industrial Initiative considers 3 or 4 systems as a reference solution: sodium fast reactor Astrid, as a first alternative lead-cooled fast reactor Alfred, supported by lead bismuth eutectic radiation facility Mira, and as a second alternative gas-cooled fast reactor Allegro. In addition, in this block of projects, I'm going to mention Generation 4 molten salt fast reactor, MSFR. This system is mentioned in as an ETP SRA annex as a very attractive long-term option. Okay, it was just discussion about perspective of MSFR to become a real ESNI system. And also I will talk about Generation 4 European sodium fast reactor, which is not demonstrator, which is industrial size system, and Swedish advanced lead reactor sealer. So since late 2011, EU framework program supported 9 projects on these systems, and the plan for next 20 minutes is to present these projects very briefly in terms of a kind of fact sheet and main goals and selected results. I don't have time to present, perspective and recommendations, so please look at the paper where it is presented in more details and then summarized. So this table shows the time frame. So it started, this project started in late 2011, 9 projects. I arranged them chronologically according to the end moment of project, except Allianz and Vinco, which were both Allegro related and which were a kind of two parts very much following up each other. Okay, so myself, I'm, as already mentioned by Frank, I'm responsible for ESFA Smart project. I and my team was involved in some of these projects, but not all of these. So then I mean that definitely I will not be able to answer all questions, but I promised to my co-authors that I can redirect difficult questions to them. Okay, let's start. The first project is Sargent 4. The total name is Proposal for a Harmonized European Methodology for the Safety Assessment of Innovative Reactors with Fast Neutron Spectrum, planned to be built in Europe. So this project was about safety. It was 2 years project, started in 2012 with a budget slightly more than €1 million and with EU contribution almost 100%. It focused on 4 ESNI systems, so highlighted with a green frame. The domain was safety, so it was, the project included 22 partners from 13 countries and was coordinated by IRSN. The main goals were to identify critical safety features of selected Gen 4 concepts, relying on the outcomes from existing FP7 projects, to develop and provide safety assessment methodology relying on legacy from international organizations, national practices, etc., and identify open issues in safety area to provide a roadmap and preliminary deployment plan for fast reactor safety related R&D. So the main selected results were were that safety issues were identified for ESNI systems. List of initiating events were identified and categorized according to their occurrence frequency. And most importantly, commonly agreed methodology for safety assessment of ESNI systems was developed, mainly based on integration safety assessment methodology developed or compiled in Generation 4 International Forum. Okay, the second project called SEALER, and the total name is Seismic Initiated Events, Risk Mitigation and Lead-Cooled Reactors. It was a 3-year project, started in late 2011 with a budget of slightly more than €4 million, with EU contribution of almost 3 million. The focus was on lead-cooled reactors, Alfred and Mira, and the domains were design, R&D, and safety, and R&D focused on seismics. It was very much focused project with 18 partners from 9 countries, coordinated by ENEA, Italy. The main goal was to develop and experimentally qualify seismic isolators for lead-cooled reactors. Okay, important to mention that this work was relevant, of course, to other nuclear plants, to other ESNI systems. But for heavy metal reactor with a big inventory of coolant, it was especially important. So selected results. The main result is that 2 isolators were designed, manufactured, and tested in different sizes up to the full scale. So this picture shows some example of real equipment, some seismic tests, and specifically high damping rubber bearings and lead rubber bearings were developed respectively for LC and MIRA systems. So LC is European lead system, which is industrial size lead-cooled reactor. Then the second result we can mention is that prototypes were subjected to three-dimensional dynamic tests under the real service loads up to failure. So the load was big enough to make this isolator failed, and it was demonstrated that the load was several times higher than design level. So it was a real experimental demonstration of reliability and acceptability of the developed isolators. And finally, cost-benefit analysis of seismic isolation adoption was conducted. The next project is now, we shift to gas-cooled fast reactor area. It's Allianz with the name Preparation of Allegro, implementing advanced nuclear fuel cycle in Central Europe. 3-year project started in 2012 with a budget of about 1.5 million with slightly less than 1 million contribution from EU. Focus was on Allegro. The domains were quite wide. It was about design, R&D, safety, and even licensing. In particular, R&D areas focused on thermohydraulic and CFD and neutronics. There were 9 partners from 6 countries, and the project was coordinated by MTA EKA Hungary. The main goal was to continue elaboration of basic documents needed for high-level decisions and licensing of Allegro gas-cooled fast reactor demonstrator. So the selected results are that new strategy for developing Allegro reactor was prepared and accepted by partners. It was mentioned by Noel, the reduction of power, in particular the change of fuel. It's new strategy developed in this project. Then new systematic roadmap was prepared to cover all design, safety, and experimental aspects of this program, of this reactor, and different governance models for Allegro implementation were discussed. As I already mentioned, the follow-up of Allianz was Project Vinco. The name is Visegrad Initiative for Nuclear Cooperation. It was 3-year project, started in 2015 with 1 million budget, 100% financed by EU. Was focused on Allegro, and domain was R&D with focus on thermohydraulics. 6 partners from 5 countries, and the project was coordinated by NCBJ Poland. The main goals were to develop principles of cooperation and rules of access to existing and planned infrastructure, to identify specific objectives of R&D activities in cooperating countries, to describe and analyze existing research, training, and educational equipment and capabilities, to determine investment priorities in cooperating countries, and to set up joint research, educational, and training projects. So as selected results, I can mention that possible international cooperation scheme in V4 countries identified. So V4 countries is Czechia, Slovakia, Hungary, and Poland. Then neutronic and thermohydraulic benchmarks were conducted related to core behavior of Allegro. And then education and training and dissemination activities includes summer school workshops and exchange visits in particular were organized. So next project is Jasmine. The total name is Joint Advanced Severe Accident Modeling and Integration for Sodium-Cooled Fast Neutron Reactors. So we moved now to sodium with the focus. So relevant reactors from our list are Astrid and European Sodium Fast Reactor, ESFR. It was more than 4-year project, started in 2012 with almost 6 million budget and 50% financed by EU. So these domains of interest was R&D and safety, and for R&D the focus was on thermohydraulic and CFD, neutronics, fuel, source term, and multiphysics. So it was about severe accidents and cold developments. 9 partners from 5 countries, and coordinator is IRSN France. So the main goal of the project was to enhance current capability of analysis of severe accidents in sodium fast reactors by developing a new European simulation code called ASTEC-NA from existing ASTEC platform developed by IRSN and GRS for LWRs. So as a selected results, we can say that new models for this code, for this new code was developed, verified, and validated, including thermohydraulic models, fuel thermomechanical models, fission gas behavior and point kinetics models, and sodium pool fires and aerolization models. So the figure shows these different parts of this big code system and interaction between them. Next project is ESNI Plus. It was the biggest project. Okay, it has the name ESNI inside, and the total name was Preparing ESNI for Horizon 2020. 4-year project started in 2013 with more than 10 million euro budget, and with more than 6 million out of these 10 of EU contribution. The domains were R&D safety, and R&D focused on thermohydraulic instrumentation, neutronics, fuel, seismics, and multiphysics. The focus was on 4 ESNI systems, Astrid, Alfred, Mira, and Allegro, and 36 partners, so the biggest consortium from, 36 partners from 16 countries, and the project was coordinated by CEA France. The main goals was to develop a broad strategic approach to advanced fission system in Europe in support of ESNI within the set plan. And the second part of the project was, the goal was to perform R&D in support of the ESNI demonstrators. So selected results was coordination between ESNI, European Commission, and national programs was analyzed, and topics for joint programming were identified. The challenges for future financial and legal models for ESNI was identified, radiation infrastructure in Europe reviewed, siting and licensing requirements for the new generation of fast reactors were analyzed, existing supply chain reviewed to support deployment strategy for fast reactors, potential of small modular fast reactors and cogeneration fast reactors in Europe were investigated. In technical parts, we started and conducted benchmarks on co-physics for ESNI systems. Important activities was MOX fuel properties measurements. So it was to mention that we try to keep this activity through following up projects. So we are continue now these MOX fuel properties measurement activities in ISVA Smart project. And also R&D on seismic isolators and selected instrumentation were performed. And again, it was follow-up of Sealer project, which I mentioned. So the 7th project is SISAME, and the name is Thermohydraulic Simulation and Experiments for the Safety Assessment of Metal-Cooled Reactors. 4-year project recently finished, so it started in 2015. With a budget almost 7 million and with more than 5 million contribution of EU. So it was liquid metal cooled reactors. It means Astrid, Alfred, Mira, ASFR, and Sealer were relevant. The domain was R&D and safety, and R&D focused on thermohydraulic and CFD. 23 partners from 9 countries, coordinator is INEA, Italy. The main goals of SISAME project were to develop and validate advanced numerical approaches for design and safety evaluation of advanced reactors, to achieve new or extended validation by creating new reference data, and to establish best practice guidelines, verification and validation methodology, and uncertainty quantification methods for liquid metal fast reactors thermohydraulics. So some examples of CFD analysis of measures and designs and some results shown here. Selected results, validation base was extended for turbulent heat transfer. This is important niche, important contribution to existing validation. Data in mixed and natural convection regimes and for geometrically complex cases. Then the combination of experimental data and high fidelity numerical simulations was set up for wire-wrapped fuel assemblies used in most of the liquid metal fast reactors in ESNI systems. Then liquid metal experiments for pool thermohydraulics were performed at different scales. The validation data were provided in loop scale for validation of system thermohydraulic codes. Then for education and training, a number of lectures and workshops were organized. And last but not least, the textbook was published named Thermohydraulic Aspects of Liquid Metal-Cooled Nuclear Reactors. So it's available now online. And some examples of CFD models of alpha-red primary systems shown here. The AIDS project is SAMOFAR. The name of the project is Paradigm Shift in Reactor Safety with Molten Salt Fast Reactor. 4-year project still running. It's finishing July next month. 5+ million euros with more than 3 million euros contribution from EU. So the focus is on molten salt fast reactor. Domains are design, R&D, and safety. And in R&D, in this project, we looked at thermohydraulic and CFD, neutronics, and multiphysics. 10 partners from 6 countries, coordinators, TU Delft, Netherlands. So the main goals were to deliver experimental proof of concept of unique safety features of MSFR, to provide safety assessment of MSFR for both reactor and chemical plant, to update conceptual design, and to create momentum among key stakeholders. Selected results include that MSFR design, including the emergency draining system, was updated and assessed. So it's shown here, the concept of emergency draining vessel. Then plant simulator was developed and used to define reactor control strategies and procedures. Risk assessment methodology was developed based on ISM. Setup was constructed to study actinides and molten fluorides and to synthesize actinide fluorides, so it was experimental part of the project. Also experiments on fuel salt vaporization were conducted to reveal retention properties at high temperature. Test facility was made to measure viscosity of salt. Several facilities were prepared for thermohydraulics experiments. Transient calculations were performed. Fuel salt processing scheme was updated and thermochemical calculations performed. And also in frame of education and training, summer school and other events were organized. So last but not least is ISFA-SMART running project. So ISFA-SMART stands for European Sodium Fast Reactor Safety Measures Assessment and Research Tools. We are happy to have on logo Phoenix bird as a symbol of fast reactor. Its 4-year project started in September 2017. So this autumn we will be in the middle. So it's almost 10 million euro budget with 50% contribution from EU. The focus is on ESFR, industrial scale sodium fast reactor. We look at the design, R&D, and safety. And in R&D, we have 4 packages working on thermohydraulic, neutronic, fuel, and multiphysics. We have 19 partners from 9 countries, and the project is coordinated by FISA, Switzerland. The main goals are produce new experimental data to support calibration and validation of computational tools for each defense and depth level, to test and qualify new instrumentations to support their utilization in reactor protection system. So we are focusing on eddy current flow meter here. To perform further calibration and validation of computational tools for each defense and depth level, to support safety assessment of generation for sodium fast reactors in general, including ASTRID or other options of sodium fast reactor, and we use here both experimental data produced in the project and legacy data. Then one of the main goals is to select, implement, and assess new safety measures for ESFR. So we make new step after CP ESFR design in development of this concept. And finally, we aim at strengthening and linking together new networks, in particular, network of sodium facilities in Europe. We have 4 sites in Europe, 2 in Germany, in France, and in Latvia with sodium loops. And we would like to make this network available for students to make we support them with mobility grants to let them spend part of their PhD at these facilities making experiments. So as selected results, we are not finished, but still during the first year, we managed to propose a set of new safety measures. So we developed a lot of CAD design in terms of CAD drawings. You can see here the new design with a lot of details. And in particular, we proposed a new low void core, and we evaluated the performance of this core during base radiation. So we arrived at some end of equilibrium cycle state and confirmed the good or improved safety coefficients of this core. We also started benchmarking of neutronics, thermohydraulics, fuel performance, and severe accident codes. It's important activity. In particular, I would emphasize that for fuel performance benchmark, we collected the main players in Europe, and we performed base radiation evaluations. Then we launched new experiments related to SFR safety. Okay, so the summary, since late 2011, there were 9 European projects related to ESNI, Generation 4 systems, so covered 7 fast spectrum systems with 45 million euro of total budget, including 28 million euro of Euratom contribution, which we are very happy, very grateful to acknowledge this support. 64 organizations were involved from 20 countries. It's very impressive. So the focus was on design, R&D, safety, and licensing aspects of these 7 systems. And R&D focused on thermohydraulics and computational fluid dynamics, fuel, seismic multiphysics, source term, instrumentation. And on this diagram, I tried to show where different projects contributed to which system and to which domains. So thank you very much for your attention.
Dr. Mikityuk, for having been so efficient, I would say, in covering such a wide span of research, 9 projects in not even half an hour. So that was very interesting and also very efficient in the way you addressed it. Are there any questions to Dr. Mikityuk? Conchita.
Yes, thank you for the presentation. Margaret McGrath from the Palace organization in the Netherlands. So, difficult question, but if you could pick one of the technologies that you think the most progress has been made on from this combination of different projects, I'd be interested to hear. And if you could again say in one sentence what you think the biggest progress within that technology has been.
This is a difficult question.
Of course.
Because I'm coordinator of one of these projects. So I have favorite system. You ask me personally,
yes.
Not on behalf of the community, because
no,
they will not be happy with my answer.
I can only ask you personally, okay. So you have to pick your favorite child.
Okay, in my opinion, sodium fast reactor was probably obtained the biggest attention and the biggest development. So partly because of the Astrid program, because a lot of projects I mentioned was run in parallel and in strong cooperation with Astrid, and was supported by France, by CEA, EDF, because it allowed to extend and make Astrid program international. And so this was very efficient cooperation, in my opinion. And this allows us to make a big step. I don't know, yeah, difficult. I can say low void core for SFR, in my opinion, probably. Yeah. Well, if I would think a little bit more, probably I will change my mind. But okay, low void.
Yes, but it's exactly in the same direction as the previous one. But I wanted to hear from you from another angle, because you were involved on some of these projects. So now I understand the sodium is the one that you have worked most. So what was, because it's a long time, so it's almost 10 years, quite a sizable budget spent on all these projects. And I guess on sodium, if we go in details, maybe a little bit more with respect to the other systems, but I'm not sure. I'm just from what I've seen here. So in your opinion, in this 9 years, what were the breakthrough that you have achieved? So a highlight, because there were no highlight in your presentation, but just one after the other. Even we couldn't recognize a connection between one and the other. So maybe on the basis of the experience, of your personal experience, can you tell us where are the connections and where are the breakthrough?
What's so difficult?
Okay, I mentioned, in fact, one highlight, which is measurements of MOX fuel properties. So probably I will answer like this. Because these activities were started even beyond this time period. It was CPSFR, if I'm not wrong, probably it was before. But in CPSFR we had a work package on MOX fuel properties measurements, which included always MOX fuel transportation between France and Germany. So it was like samples, MOX fuel samples transport from fresh and irradiated in Phoenix, transported from basically Kadarash to Jersey, Karlsruhe, and then the thermophysical properties were measured. And first of all, thermal conductivity as function of temperature, plutonium content, stoichiometry, porosity, and burn up, of course. So in every project, it started from CPSFR, then SNI Plus, and now ESFR Smart. And now I know there will be new proposals to continue this line. In every project, we added 1, 2, 3 points to the database. And I think nobody will refuse that this is extremely important and extremely difficult and expensive activities and needed.
Thank you, Dr. Mikitu. Before we move to the next subject, well, we have no time, so please. Part of my answer under the control of Dr. Mikituk is that some of the progress is not visible. For example, things like harmonizing, let's say, objectives for fast Newton reactor safety, let's say in Europe. Well, it is something that is not visible really on a view graph. Also, we should remind the fact that SNI was launched 10 years ago. Before that, it was politically not accepted that we would really cooperate in Europe for future nuclear energy systems. And then there was no cooperation on fast. There were bilateral or multinational cooperation, but not within And I think that besides sodium-cooled fast reactors, that was really on the track. So the emergence of lead-cooled fast reactors or molten salt reactor is part of the, let's say, path that has been achieved in over the past decade. Even though, let's say, this is just the beginning of the story in terms of building competencies and building, let's say, research facilities to be debated. Thank you again, Constantine. And now from fast reactors, we move to the nuclear fuel cycle. And the next presentation will be delivered by my colleague, Stéphane Bourg. So from CEA, he's a project manager in charge of international cooperation at CEA Research Department of Mining and Fuel Recycling Process. Stéphane has worked on pyrometallurgical reprocessing in the early 2000s and was since 2008 the coordinator of the European research projects about hydro and pyro separation process development for spent nuclear fuel reprocessing. So the projects accept success engineers that he will cover. Beyond that, his research activities also cover life cycle assessments of energy systems and raw materials value chain analysis. Stéphane, please.
Thank you very much, Frank. Good afternoon, everyone. Since yesterday, we heard a lot about the interest of nuclear energy for climate change, for sustainability, and also we heard a lot about machines, reactors, their safety, their efficiency. But if I could make a comparison, I think that we discussed a lot cars without building any roads. And what I will show you now is how can we build roads, that is the fuel cycle that we need around these reactors through 3 projects. But before, I will present you an introduction to position the fuel cycle and how this fuel cycle can really bring the sustainability in the system. And then I will present you rapidly. You will see a lot of slides just to illustrate the main highlights of the different projects. So as an introduction, there are different ways to operate the fuel cycle. The first one, the most applied in the world, is the open fuel cycle. If I could illustrate this with the French situation, if we imagine that the French fuel cycle is an open fuel cycle, we would mine about 10,000 tons of natural uranium just to prepare 1,200 tons of spent fuel and just to burn 70 tons of uranium. So it means that the global efficiency of the use of the uranium resource is less than 1%. So today, if you explain me that nuclear energy is sustainable, I don't follow you. So how can we increase this sustainability? The first way is what we call the twice through cycle, so the twice through cycle or the French fuel cycle. By using this spent fuel once as a MOX. With this, in France, we can save about 20% of the natural uranium resource. And then, wow, we have a global efficiency of the uranium resource of 1%. Great, from 0.7 to 1. But we are far from a very efficient use of the uranium resource, which is a limited resource on Earth, of course. And then the next step, we are discussing this for 2 days almost already, is the fast neutron reactors. They totally change the picture, of course. As you know, fast reactors can use efficiently the 2 isotopes of the uranium, 235 for the fission, 238 for the transmutation. And if we try to imagine what would be the efficiency, the global efficiency of all the fossil resource we have, in an open or just thermal fuel cycle, you can see that the potential reserve of the uranium is almost nothing compared to the energy that we know today on coal, oil and gas. However, if we move to the fast neutron fuel cycle, then the same amount of uranium can produce much more energy, and then this uranium resource become the main reserve for producing electricity. So it's a total change on the paradigm if you move from the thermal to the fast fuel cycle. But to do this, we need the relevant processes, the relevant fuel fabrication, fuel reprocessing, and waste management. And the next step, it was also discussed in some workshops, is the long-term waste management with the problem of the radiotoxicity and so on. If we really look at this radiotoxicity, we know that once the plutonium is removed, the next contributor is the minor actinides and mainly the americium. And therefore, if we want to improve again the fuel cycle with a fast reactor, this is by managing the americium, by the transmutation of the americium. And therefore, we will save the waste repository resource in a deep geological repository strategy. But what has to be understood is that if we work on the life cycle assessment of all these different fuel cycles, and if we want to know more, I mentioned 2 papers addressing the current fuel cycles and future fuel cycles. In fact, and if we normalize to 1 the open fuel cycle, you can see on these pictures that if we close the fuel cycle on the French way, we already reduce the impact of the nuclear energy by 20%. In fact, mainly what we gain from the mine. If we go to the EPR, very efficient transformation of heat into electricity, then we save again some impact. We reduce the impact. When moving to the fast reactor, we change the picture. In fact, with a fast reactor, and if you have already depleted uranium, you don't need any mine. You don't need mines anymore. And most of the impact of the nuclear energy today is the mining. Okay? So a total change in the impact. So this is very important. But you can see that if you transmute the americium, in terms of environmental impact, there is almost no advantage. So transmuting the americium is not something that will save any resource, that will reduce the environmental impact of the nuclear energy, is just to address the societal acceptance of the nuclear waste management. It could be another debate. And this is it's clear when you look at the amount of waste produced by the different fuel cycles. At the end, in terms of waste, these fuel cycles are not very different. The amount of waste is almost the same each time, even higher with the fast reactors compared to the thermal reactors. What is different is the typology of this waste that will require a lower space, a lower volume in the deep geological repository, not because of the radiotoxicity. The clay doesn't care of the radiotoxicity, just because of the heat load. And then, if we want to implement these different options, then we need the fuel cycle. We need to address the fuel fabrication and the fuel reprocessing with the dissolution and the refabrication. And if we look at the different systems that we can address, and if we look at the fast reactors plus the ADS, some of them use MOX fuel, others can use carbide or nitride fuels. I did not mention metallic fuels that are studied in the US, but poorly addressed in Europe. And the molten salt reactor, that's different and are not in the frame of the projects I will mention. So, what are the common pictures of the projects I will present you? But it's the fuel cycle. That is, we need dissolution, separation, conversion, fabrication, whatever the fuel cycle, whatever the fast reactor or the ADS. And this is addressed, or this has been addressed by Success and Asgard some years ago, and now the follow-up of Success being Genius. A lot of separation processes have been developed for the last 25 years in the world. These separation processes could be applied to the different fuels, whatever carbide, nitride, or oxide, if we well master the head-end step, that is the dissolution. Once the fuel is dissolved, we can apply, I would say, whatever separation process. So a key issue is the dissolution. That can be a real issue for some fuels. And then also the different processes must address the different options, because we are here to provide solution to the policymakers. We are not here to decide, and therefore, by developing our processes, we provide solutions either for the what we call the homogeneous recycling, all the actinides, including the minor actinides in the fuel of all the assemblies, or an heterogeneous recycling where the americium, for example, is transmuted in Mira or in blanket fuels in fast reactors. So first, Asgard, from fuel to fuel for the non-MOX advanced fuel. This project was managed, coordinated by Chalmers University, and Christian Egberg was the coordinator. And Theodora is here if you have some question on this. You have here the budget, a huge contribution in kind from the partners is the key parameter. I will not read everything for you. The focus was, as I said, on advanced fuel and also for the transmutation, that is CERMET and CERCER. And also training and education, but I will come back in the end. So first, the CERMET, first issue, the dissolution. So in Asgard, model systems were first studied, so cerium, molybdenum, then non-irradiated samples, plutonium oxide, molybdenum, and then irradiated samples from PETEN, where there were in these samples both plutonium and americium. And the real issue were identified on the very difficult way to dissolve these targets, in particular with the plutonium, very difficult to dissolve. We know with the classical fuels that when you have both plutonium and molybdenum, it's always very difficult. Second, CERCER. So here it's oxide of actinides in a magnesia matrix with different studies that were performed in order to study the dissolution speed, the effect of the acid, the reaction between the MgO and the media, the dissolution in the model system, and therefore the conclusion that we had in mind, but that it's easier to reprocess a CERCER than a CERMET. However, the question will be the management of the magnesia as a waste. It will be very difficult to recycle it to prepare fresh fuel, so it will be a waste. We know that it's compatible with glass, but in low amounts, so we could imagine a huge amount of waste produced with this fuel. Next step, after the separation that will be addressed in the other processes, the refabrication, the first step being the conversion, how to go from a solution to a solid with mastered properties, and different methods can be used for this based on non-powder approach. One is the salt gel methods, another one is an impregnation of solid matrices, and the last one is the photochemical conversions. So these three options were studied in Asgard. For the fabrication, today the issues were on the nitride first. So studied on the fabrication of nitrides from salt gel or from powders. And with one issue is the measurements and the reduction of the amount of residual carbon in the fuel. Here I think Janne is somewhere maybe and is the expert in this kind of fuel. And for the dissolution of these materials, they had the opportunity to work on the real fuel from the confirmed experiments. And you have here the results of the dissolution. It's not very easy, and the hydrofluoric acid was necessary to get a total dissolution. The next category of fuel is the carbide fuel. We know by experience that carbide fuel is quite easy to dissolve. However, there is the problem of the carbon here, that at a classical dissolution produces organic species in the dissolution media, knowing that these organic species can interact with the organic solvent that we use for the solvent extraction. So the issue to fix when we want to reprocess a carbide fuel is how to remove the carbon or how to limit the impact of the residual carbon. So two options were studied. The direct dissolution is the first one. And there are some papers that have been published based on these results, and that's it. And there is a second option, but I have no time to describe it. It's by oxidation. It's violent, but it's very effective. So this was a very brief overview of Asgard. There is a poster for those who want more information on this project. And next is the core of the systems is the separation processes that have been developed first for preparing, I would say, the first fuel of the fast reactors, that is from the light water reactor fuel. This is success. And in the next step is Genios, is the multi-reprocessing of the MOX fuel. So in success, so I would say improving the safety of spent fuel reprocessing. It is the safety not in the reactor this time, but in the reprocessing plant. And all the R&D programs were driven by safety issues. So the project had 26 partners, a total budget of 10 million for a EU grant of 50% of this total budget, and collaboration with Japan and also with the DOE. We had for the first time an INERI project between the DOE and a EU project. So this was a very useful contribution you will see in a few slides. So in success, we addressed separation processes for the two options, the homogeneous recycling or the heterogeneous recycling. The homogeneous concept is named GANEX, and the heterogeneous, two options, SANEX, if you want to transmute both americium and curium, and EXAM, if you only want to transmute americium. In success, what did we do? We stabilized, I would say, the different flow sheets for the three options. And so an ISANEX process with a hot test, a EuroExam process, the most challenging, and the EuroGANEX, knowing that the hot test, the first hot test was done at the end of the previous project, and we used the results of this hot test to improve the EuroGANEX flow sheet. I will not enter in all the detail, but if we just focus on the safety, the main issues in the reprocessing is the issues linked to the radio degradation of the media, whatever the aqueous phases or the organic phases. And therefore, we have to understand what happens when an organic phase degrades under irradiation. Because new species are created. Gaseous, so risk of increases of pressure, or still in the solution, and then potentially extracting some species, more than the reference system, or extracting species that we do not want to keep, or increasing the interaction between the aqueous and the organic phase. We call it the third phase, or the red oil, if we go to the old Purex process. So and the real safety issues with this. So a lot of studies were done on the radiolytic stabilities, and these data are really important. And what we particularly did with our American colleagues is to compare different techniques for assessing the impact of the degradation. In Europe, we worked on the static tests made in CIEMAT with the NIADE facility. And in the US, at Idaho National Lab, there were some dynamic tests on the irradiation loop. And we have demonstrated that the behavior of the systems is totally different in the two media. And with this, finally, and it's good for processes, in a real system, the molecules are more stable than in a closed system. So this is a very important result that we get through the collaboration with the US. I will come back to these loops. It's a key tool for the studies of the safety. EuroExam, so it was the first process was developed at the CEA. It's very complex, a lot of stages. So there was a concept of a simpler process based on a new molecule named TPAEN. And through the collaboration, it was possible to implement a spike test of this process at Jülich. So two tests were done and demonstrated finally the low reliability on this system. That is, the data at the lab scale were very, very good, but once we went to the spike test, we highlighted a lot of drawbacks coming from the purity of the TPAEN, coming to the sensibility to some parameters, and therefore we decided to maybe forget the TPAEN and look for a new system, and then this is now ingenious. Just one slide to also mention that in success there was a part of the work dedicated to pyrochemical separations. And I have highlighted this by one work that was done at ITU. Sorry, I will always call this center ITU. It will be impossible for me to change this. At ITU, And what was very nice, through the collaboration with Japan, to make a test of a process concept on irradiated fuel, the metafix fuel that was irradiated in Phoenix. So demonstrating the efficiency of a new separation system based on the use of liquid aluminum. It would be too long to explain. Also, publications are existing on this process. We had also system studies in order to know the maturity of the different processes, in order to orient the R&D program. And if you want, you can download a book from the success.eu website. Is a roadmap comparing the different processes developed in the world and proposing and explaining their level of maturity. So you can download this book, go to the website. And also global safety studies under the piloting of IRSN. They come with us for explaining us methodologies, managing workshops, brainstormings, in order to help us identifying some weak points in the different processes, again, in order to orient the next R&D programs. And then Genius, based on the result of success, but this time saying, okay, we prepared the load for the first irradiation, but now we have to reprocess. It means that the new MOX we have to address is not at 8%, but maybe at 22%. The dissolution is more difficult, and the concentration of the solutions are higher. It means that we have to go deeper in the understanding of the chemical systems, in their stability, and in the different chemical risks that could arise from this. So, Genius is organized on the idea of a well-established scientific understanding of the mechanisms, is the green line. When we know very well the different systems, then we go back to our flow sheets and we try to improve them. And after we integrate all these results in system studies to evaluate the new process. So the project started in 2017, 24 partners, 75 million budget for a 5 million grant. And again, a new INERI project with the DOE to continue the collaboration on different issues, but mainly on the radiolytic stabilities. And the idea of Genius is based on what we know, is to go by down selection. We will not decide on what is the best, but we are cutting some options because we consider that they are not appropriate for the future. And then at the end, what will remain is few options on which we are really relying for the future. And just to illustrate how do we work in Genius and what are the first results. We looked at the Euroganex. It works very well. It's very efficient. But, however, to make it efficient, we had to find some compromises that at the end are not very convenient for a large-scale implementation. We use a molecule that is named TODGA. It's very efficient to extract lanthanide and actinides. The problem is that it's not very good for managing the plutonium. There's very low loading capacity for the plutonium. And to optimize this, we had to mix another molecule in the system, DMDO-HOMA. So the system is a little complex. Here also, this increases the density of the phase. It increases the viscosity of the phase. So this is the first drawback. The second drawback is that we use a molecule in the first feed to keep some fission product in the initial solution and avoid any contamination. So this molecule is the CDTA is not so efficient. Also. We need a lot of it. And last, to recover selectively the transuranics, we use a molecule. Maybe you don't see it very well. These molecules that name SO3-BTP has a lot of sulfur atoms. And sulfur atoms could be an issue at the conversion when we will go from the solution to the fuel. So maybe this also is something to be fixed. Then what did we do? We went to the problem of the TODGA and we say, wait, how can we combine the effect of DMDO-HOMA and TODGA in one molecule? And by understanding the effect of the different branches on the molecule, we were able, or the University of Twente with the GRC at ITU were able to propose a new molecule that fixed the different issues that we had, and now this molecule, MTDDGA, does not need anymore the use of DMDO HEMA. So the system is simpler to use. And maybe for you it's not very important, but the plutonium loading limit went from below 20 grams per liter over 32 grams per liter without any third phase formation, whatever the concentration. So this is something that is really important in terms of process safety. Next, irradiation stability. What we mentioned previously is we are missing loops. And therefore, in Genius, we are working in comparing the different loops that exist in order to check their different properties, and then for the future, if someone wants to build a new loop, what would be the best option for having results very interesting and comparable to the rest. And this job is made together between Genius and the DOE, and we had already different workshops, brainstorming, and we are now organizing a round-robin test on the same system, in the same conditions, but on the different tools to check the differences. Replacing the SO3 BTP is the next step, and here also, thanks to our Italian colleague, a new molecule has been proposed, is the PTD. It's only based on CHON atoms. It means that as this molecule will remain with the actinides even at the conversion step, when we will burn the system, we do not have this sulfur atom remaining. Sulfur atom has some issues after under irradiation. There are some activation products, and so it's an issue. So here we don't have this. So this is the big also achievement of Genius, and with also the chance to carry out some experience by exchanging researchers between Politecnico di Milano and the CEA, and the people from Politecnico di Milano were able to work at the CEA with quantitative amount of americium and a high loading, macro concentration, that is, of course, not possible to be done at Politecnico di Milano. The ISANEX process is also under improvement, based on the results we have also for EuroGanex. The two processes are not very different, but we take the opportunity of improving GANEX to improve also ISANEX. I will not enter in the detail. And the last is the new Euro exam that for the moment is named AMCEL. And here also the idea was to find another molecules instead of the TPAEN that does not work very well. And the molecule is proposed here is an SO3-BTBP. So there is a sulfur atom, but for the moment we did not find any CHON molecules doing the job. So as we need a process, this is the option. And it will be tested as a spike test at Jülich by the end of the project. There is a backup option that is also understudied at Chalmers. How many times I still have? Okay, perfect. It's finished. This is a very innovative process. On the paper, it's much simpler, but now we have to go to the demonstration. System studies to integrate the results, process safety also to orient the R&D, fuel cycle integration to discuss with our stakeholders, and that's it. So training and education, a lot of schools have been organized, often between the different projects, student exchanges between the partners, scientific seminars, of international scientific seminars, both in Success and in Asgard. And in Genius, we had already what we call a radical behavior workshop that we held last year in Würzburg with more than 100 attendees. So again, this is thanks to the training and education budget allocated within this EU project. Thank you very much.
Thank you very much, Dr. Bourg, for this very impressive overview, and very impressive also in, let's say, giving examples of, let's say, designing and synthesizing, let's say, new molecules that, let's say, new daughter molecules that really keeps the attractive features of parent molecules. So that seems to open a new way of a new path for research in this field. Are there any questions for Dr. Boom? Yes, there is a question over there.
Yes, so you know my name by now. Out of the processes you study on americium extraction, which one what do you think has the greatest potential for industrialization?
Today, if we want a process for americium alone recovery, knowing the maturity of the different system, I would use the one that was initially developed at the CEA. But just because we have not demonstrated AMCEL for the moment, it would be a mess. It's very, very, very difficult to master, to control, to monitor. But if we would need americium alone today, this would be the option for quite a large scale. After, if you want a small scale, solid liquid separation, it has been done for years. We know how to separate americium from plutonium on resin columns. Well, after you have to manage the resins. It's another topic.
Other question for Dr. Boer?
Curium. The curium is managed by the ISANEX process. So we can recover americium and curium. It's easier than recovering the americium alone. But today, everybody considers that it's of no interest because managing the curium in the fuel cycle would be a real mess. In the plant, biological protections, for the radiolytic stabilities of the system, so a lot of waste generated by the process waste, and also at the fuel fabrication. And also, you know that in all these concepts, there is an interim storage between the time you go from the waste, and the repository. And it's much easier to manage the curium by the interim storage than by transmuting it. Because do not forget that what is not in the deep geological repository is on the plants. And if you want to calculate the inventories of all the actinides that will be in the plant, if we go into the transmutation of the americium, I'm not sure that it will help in the acceptance of the nuclear energy.
Thank you, Stéphane. Now let's move to the next presentation. Do you have a question? Okay.
Just a short comment to what Stéphane just said. Actually, we can separate curium from americium. We know that usually you extract them together. They go always in parallel. But we obtain D values higher than 7. That means when you go over 1, you can already extract, even if you need several stages. But now we are up to 7, which is much, much better than we had in success when we had 3. So it is possible, but as Stéphane said, the amount of waste will be significant.
The CA process D is 2.6, but then after you just master it by chemical engineering.
Thank you. Let's move to the next presentation that will address partitioning and transportation, contribution of MIRA to a European strategy for high-level waste management. And the presentation will be delivered by Professor Dr. Hamid Ait Abderrahim. I don't think Hamid needs to be presented, but still, I just mentioned the fact that he's a Deputy Director General of the Belgium Nuclear Energy Center of Mol, that he has been project manager and project director for about 20 years, the project of the experimental ADS MIRA, which was recently granted 558 million euros for the 20 coming years. And also Hamid is a professor of nuclear engineering at the École Polytechnique of the Catholic University of Louvain. Please, Hamid.
Thank you, Frank, for the nice introduction, and dear colleagues. So, you see the title of my presentation. I have 7 projects I have to report on, and I have to tell you what is MIRA and how it contributes to the strategy of the high-level waste management, and all that in 20 minutes if I want to respect the time of the break, or 30 minutes if I want to respect the time I was allocated. So I will choose 30 minutes. I apologize. I'm starting 10 minutes behind. So, first thing, to see here the 7 projects that I will report, you will be asking me, what is the link between all those projects? To avoid this question, I will tell you. M of Mirt is Mira. M of Marisa is Mira. The second M of Maxima is Mira. The H of Search is heavy liquid metal. The M of Max is Mira. The Y of Freya is hybrid, and I think Mira is a hybrid reactor. And the A of Arcas is ADS, and I think Mira is the only ADS in the game. So, that you get rid of that question. One thing I want to recall, the amount of fuel that we are loading from our, I can look there, from our nuclear fleet in Europe that represent 50% of the electricity, 26% of EU. There are half of the 28 countries having nuclear, and this represents 50% of non-polluting electricity in terms of CO2. About spent fuel, the inventory, 2,500 tons of spent fuel are discharged annually from those 128 reactors. And in terms of minor actinide, or I would say, the first thing that has been said by Stefan, we have to worry about the major actinide, which is the plutonium. You got 22.5 tons per year out of the spent fuel, or contain 22.5. And then you have only 1.2 tons of americium, and the same for neptunium, and 0.1 ton, or 0.107, I don't read correctly, for curium. It's very tiny quantity. And we have those long-lived fission products, which are 87 tons per year. So this gives you the scene. These have been shown, this graph, by Stefan, the radiotoxicity, the heat, etc. And I will come back on that, because this is for a graph for people understanding science and knowing what is science. And you see that indeed the plutonium is the major one that you have to get rid if you want to do something. Now, second thing to know, rapidly, high-level waste. Do we have solution or not? Yes, we have solution, geological disposal. Direct, put it in the ground, and you get rid of it, and normally, technically, this can work. Problem is politicians can't decide, society is not accepting, so we have to be turning her in favor and asking for it and not accepting it. So when we speak, the other thing we can do today at industrial scale, Purex, we retrieve the plutonium and uranium. So if we can find solution for plutonium, we already have done a job you have seen from Stefan, his presentation. Minor actinide and fission products, vitrified, go to the waste basket. But we have issue of time, etc. And so then partitioning. What is partitioning and transmutation has to do? Deal with some long-lived fission products and some minor actinide. Stefan said the radiotoxicity is not an issue. That's true in today's studies of the geological disposal performance scenarios, because they exclude and they don't want to hear about human intrusion. Unfortunately, there are more and more people concerned by human intrusion in our geological disposal. Because the memory, you can hold it for 500 years. And after that, you will look for sources of geothermy, because it's green electricity or green energy, and you will dig in a heat source that you put yourself in there. That can be happening. I'm working in a lab where we have a geological disposal lab, and we started digging hole by our former non-nuclear activities that get separated from MOL. They have project on geothermy. They are digging holes 500 meters from our underground laboratory. They have forgotten that there is a lab there. So it's only 20 years that we separate. So 500 years can be an issue. So if we do partition, what we have to do first of all is the chemistry. It's important because without partitioning you can't do transmutation. And then when it comes to transmutation, you transmute the minor actinide by fissioning them, and some of the long-lived fission product, if you can do it, why not? And now this is the graph I showed to the politicians to understand what we are talking and to make them accepting to give you big money for your project and not for your science. First of all, you say, if I take uranium in nature, I put it in my PWR, I increase the toxicity by a factor 1,000 to get down to where I started. It takes me 300 years, no reprocessing. I do already reprocessing that I can do classically at commercial level. We know the price. You send your fuel to La Hague or to Sellafield or to Tomsk, you get it done and you pay. And brings you to 10,000 years. You do this little separation that may be complex. We don't not yet completely industrialize it. And you get 300. So that's the thing that you are doing. What you do also, you reduce then the volume that you are sending to the waste basket. You are reducing the toxicity. And as it was said, your impact on the footprint of your geological is not the factor 100, is a reduction. We calculated for us in Belgium, we reduced the footprint of our geological disposal between this solution, the reprocessing, and here we gain an extra factor of 4. And compared to this is a factor 8. So it's worth doing, especially for a tiny country densely populated. Maybe for a large country it's not an issue, but when you are densely populated, therefore you can find which countries are interested in this story. So what we concluded, this is a very long history actually by PNT in Europe and elsewhere also. Since the 80s or the 70s, we are working on this in various countries, in Europe, in Japan, in US, Russia. EC and PNT in the Euratom program, is present since the FP3 that we are receiving funding for this topic, because it is, I would say, far from industrialization and also joining effort. And also, here we started by looking to fuel irradiation with minor actinides and separation in the FP4, sorry. The conclusion that came from that period, I'm talking to the end of the 90s, was that fast neutrons are needed for transmutation. We didn't say ADS or fast reactors. We saw that fast neutrons are needed. Second thing, we do separation for minor actinide and lanthanide that has to improve with factor 30 to 50 is necessary if you want to do a treatment of the minor actinide. Another thing that has been said, if you want to deal with something, do first plutonium. This is the first thing you have to do. Then if you want to add, and it has been also said by Stefan, do americium with it. So I'm happy that people of T and people of P at least are on the same wavelength. And the other thing, we have to care if we are doing all that fantastic story, but we make a mess with the secondary waste, then we didn't solve anything. So this is already also was mentioned at the end of the 90s. And also feasibility of accelerator driven, we were just at the beginning of ADS, should be deepened because we saw figure of merits in there. So then came the FP5. FP5, we received also a reasonable amount of money. We had about 14, if I remember, projects in there, and we structured them, partitioning, then those guys related to the fuel for transmutation and the technology and material for transmutation machines, and also the nuclear data and the basic studies on support for the physics for those guys, and the design centralized on the ADS. But what was interesting to put, we put there a thematic network we called ADOPT. And I would like to point out the importance of that small project, which was €1 million, because it had a very important objective, which was Europe, there is strong interest to explore the potential scientific, technical, and industrial possibilities for PNT. And so therefore, saying if we integrate the member state and the European Commission effort, we can come to a strategy to develop in a more synergetic and fostering all this effort. And we put a specific objective for the ADOPT itself, but what I wanted to point out, we had to direct the R&D, or let's say foster the R&D with the objective of industrialization. And what we did as an outcome for this ADOPT, yes, we fostered national and Euratom R&D. Yes, we came with a strategy for industrialization. We made the links to outside Europe, but unfortunately, in the FP6, I found it personally really a pity. We splitted this partitioning from the transmutation. As I said, if you want to do transmutation of minor actinide, you have to fission them. We started by fissioning our P from the T. That's a bad thing. So that was the result. This group became Europart in FP6, and all those guys became Eurotrans, and there are other groups, other project that has been also feeding the transmutation. But the strategy is this one that we came with. Objective, be in a position to have everything in hand for industrialization of PNT. It doesn't mean you have to industrialize it in 2030, 2035, but at least you have all the elements for the decision makers. Also the economical one, because you can have nice science, you can have nice technology. If it is unaffordable, you don't make it. And that's what we said, we need demonstration at engineering level. We have to quit our labs, we have to quit our small things to go to industrial, pre-industrial scale for those 4 building blocks. The advanced separation, the minor actinide fuel fabrication, a dedicated transmuter or transmuters. We were counting on Astrid for the critical and on Mira for the subcritical. And minor actinide fuel reprocessing, it has been pointed out in Stefan, there we have still also an effort to do. And we are getting support for all these aspects in the Euratom program. Sorry, what's that? Now, so we continued the support in the FP7, that was 7, sorry, and the Horizon 2020. Those are the projects I will tell you, and I will just, there are posters on the each project, but I have to give you 1 or 2 slides about the real achievements that we got out of them. So, MIRT project, what we succeeded to do as really a result that we can use today. The accelerator of MIRA on the R&D we conducted has delivered a full design that we are executing today. The first part of the accelerator of MIRA is under construction, and the first protons of MIRA are born the 13th of March this year in Louvain-la-Neuve. Second thing, all these technologies have been demonstrated. The second thing is for the heavy liquid metal hydraulics, fuel assembly, production, and integral systems have been achieved. The chemistry of volatile radionuclide, quantification and characterization of what can come out of our field, we have them. The actinide fuels, we have also some of the fuels, especially those containing americium, that we can today have the, let's say, the qualification or the basic data for them. The Guinevere subcritical Freya delivered as extra configuration for valorizing, or let's say designing our reactor of MIRA with experimental devices in it. The courses, many courses on ADS and workshops have been organized. These are the pictures of what is already operational and building, the ECR source, the LEBT, which is producing protons, the RFQ prototype that now constructed. Now all this part is constructed in Louvain-la-Neuve, and we tested the CH cavities that we are starting to mount next month. Second, Marisa. Marisa was actually a support action for preparing the objective of MIRA to become a legal entity, etc., and how we will be running this machine. The achievements are summarized here. We have now the position for MIRA as an open international user facility, and also the legal structure has been created. It will be an IESBL non-profit, international non-profit organization. We have the MIRA management principles for the different kind of groups, so that gives you the business model of this facility that has been achieved. The financing of MIRA mechanism, we have identified them, and we have already triggered one big one that should start, which is there. The MIRA environment assessment report has been also conducted, the technical integration of the MIRA primary system also. The maxima, mainly oriented towards the safety. I listed there the achievements. I wanted, we are in Pitești, to mention this one. We conducted in the Triga ACPR, the transient on the fuel of MIRA. We have handed over here various segments where we conducted the experiments, but we have also conducted the other thing, which is the blockage scenario of our fuel assembly. We have the results now. For the other important, the steam generator tube rupture, we have demonstrated that MIRA can survive that, where there is no problem. The fuel and coolant compatibility, the tests have been conducted, and positive passive safety system for the cooling of the decay heat is demonstrated. So this is for the coolant fuel interaction or compatibility by calculation and by measurement. And this is the experiment that we have run in here, where we have used the ACPR reactor. It gives you 20,000 megawatt power in a pulse. If I remember, someone for Pitești can tell the number for the time is less than a second. We got the 20,000 megawatt pulse. Yeah, but the pulse is the duration. Yeah, okay. And we didn't succeed to break the fuel pin of Mira with those transients up till now. So we determined the limit that we wanted to have to add in our database, actually. The search, I said, was mainly for the safety aspect and for thermohydro and the chemistry. And there, the most important thing that the heat transfer of wire-spaced fuel bundle, because our fuel bundle is with the wire space, has been demonstrated experimentally, and the development of impurity and oxygen control is achieved, showed compatibility of homogeneous sintered MOX fuel with the LBE at 500 degrees C, up to 800. So we go far beyond the nominal peak temperature. We build CFD and Simmer models for dispersion in case of rupture of the fuel in the liquid metal. The measured release of mercury and polonium from the LBE have been established, and we held also workshops and lectures on this. So these are the the mercury and the polonium release, and this is the model of the heat transfer in the fuel bundle. Max accelerator of Mira, as I said, the production of a reference design for the whole Mira accelerator up to the 600 MeV, and individual components have been prototyped, the RFQ, the source, the 17 to the 17 MeV, and now we are building the first injector of Mira based on that technology to check the global integrity or reliability. These are pictures of the RFQ when we prototyped it, but now this is already fully produced. The Freya, which is the experiments in Guniver project, and there we are having several fast reactor cores were coupled to the GNP, which is the continuous generator of neutrons through DT reaction, and we simulated a lot of the configuration that we will meet in the full operation of Mira during the lifetime of Mira, with experimental devices, with the radioisotope production, with material irradiation, and so on. And also in normal and off-normal condition. Different criticality level has been looked at, between 95 and 99, but we went also to the subcritical systems for the core loading actions when we have to reload the core. So can we master that? The applicability of the different subcriticality measurement techniques are investigated, and we are feeling comfortable to present our file to the licensing authority. The Freya experiment program also regarded some LFR configuration, not only lead bismuth, pure lead. We looked at that on support for Alfred or the LC program. We were doing that. We held also workshops and lab sessions. So this is the configuration of Guniver as it exists. The central part, we extract 4 fuel assemblies to put the beam line, which brings to the center of the reactor actually the deuterons that are generated by GNP, because we do DT reaction to create the neutrons. ARCAS. ARCAS was for comparison of scenarios. Is it better to do with fast reactor, with accelerator, and what is the added value of one against the other? And what we did there, what the main achievements we consider, is that establishing a reference minor actinide stream in the different process, Second thing, we studied the homogeneous and heterogeneous transmutation in fast reactor as well as in ADS. The study in the ADS, we took for the industrial ADS the EFIT design that we have developed in Eurotrans 400 megawatt thermal. Reprocessing also, we looked to the state of the art of the fuel fabrication to define what is the TRL level we have today, how much effort we have to continue, as well as for their reprocessing of those special fuels have been looked. And those scenario studies to look a solution at the level of Europe. As I said, 14 countries having nuclear, some willing to quit, some willing to continue, etc., some willing to enter, and so we did that. But what is the contribution, all that, of MIRA then in the PNT? What I said, this is MIRA, how it will look like in Belgium. So for Europe and beyond, a sustainable and innovative application from nuclear research to industrial applications. What we got last year, September, is 550 million euro from the government, Belgian government, after having spent another 100 million euro between 2010 and 2017. And if I count all what we spent from 98, I come to something like 200 million euro. And this was mainly from SCK money, then the Belgian money, and there was this contribution from the European partner and the European programs that I was showing. And so this amount of money, about 300 million, will serving for building the first part, which we call Minerva, the accelerator up to 100 MeV and a proton target facility. This is to be built by 2026. A second envelope, 115 million euro, is to develop further the design of the reactor, and also the second part of the accelerator, there is some R&D to be conducted between 100 and 200 MeV. Because we have the design up to 600, but there are parts to be still demonstrated in the intermediate zone. We have also 156 million euro as operating costs that we secured for the period 27-38. Why this period? Because this part will be operational in 26, and we can use it already. So we need an operational cost that we secured with our government. We have also established the international non-profit organization that will be welcoming the international participation in MIRA. You will not come to invest in SCK. You come to invest in the project that you wanted to participate in, which is MIRA. And political support is guaranteed through the Vice Prime Minister, who is going to promote the project internationally. Still have 5 minutes, I think. The accelerator of MIRA, 600 MeV, 4 milliamp current, we accelerate protons. We have 2 injectors because of the reliability that we want to achieve. And we have here normal conducting up to 17 MeV, supraconducting starts here, spoke cavities, and then niobium elliptic cavities in cryomodules. We shoot the protons on the liquid metal of the reactor directly, so there is no circuit separated for the spallation target, and we got this very intense source, 210 to the 17 neutron per second in the center of MIRA. The core is subcritical, 0.95, power between 65 to 100 megawatt thermal. We can go, so the design of the heat exchangers and the cooling system is for 100 megawatt. And we use LBE, lead bismuth tactic, for the target and for the cooling. The portfolio we have, because since '98 we started the project as a research facility, a multi-purpose research facility, and therefore the design of MIRA is very peculiar compared to a compact reactor that you would do for a demonstrator. But if you want to accommodate research, you have to have space in your machine. And therefore, we are addressing all these kind of research But first of all, we motivate MIRA for the transmutation of the nuclear waste, and that is the first objective. And now, with this, we can contribute to the strategy of Europe in PNT as we are responding to the third building block, which is a demonstrator of a burner. And here, this is a result from ARCAS when we compared fast reactors and ADS. Fast reactor can do the job. They can burn very good the minor actinide, except that due to the safety constraint, because the low beta effective of your minor actinide, you can't load large quantities. So, and we came to the conclusion we can burn 2 to 4 kilograms per terawatt hour in the sodium fast reactor, the ESFR that Mikichuk was presenting. And in the EFIT, we can go to 35 kilo per terawatt hour. So then you can imagine that countries willing to leave nuclear energy are more interested in that story if they want to get rid of their nuclear waste more rapidly. And actually, this is the other thing that we did in Pateros. We grouped the countries willing to quit nuclear under category A, and those continuing under category B. And what we showed that despite this difference in nuclear energy policy, we can work together. And we can share those facilities. For countries A, the gain for them, they can more rapidly make their minor actinide disappearing. They can switch the plutonium to the countries willing to go further with nuclear, because plutonium is a resource, is not a waste. And another thing that we have shown, that the size of the fuel cycle, cleaning the end of the fuel cycle, will be very reduced. Yesterday, in one topic, they were talking, what about multi-transport around Europe for this issue? And so there you can clearly do the job in one centralized place. Why? You see here, with 15 units of EFIT, you can burn all the minor actinide of the countries A willing to quit, mainly Germany, Belgium, Spain we put at that moment in there, and we put Switzerland in there, and those willing to continue. It took them, with 15 EFIT, 32 years to get rid of the minor actinide stock they will be accumulated. And the countries willing to continue nuclear, they stabilize, they stock 200 tons in the cycle. And so now the question is this big or not? 15 EFIT, my God, this is huge. Look this table. Little tiny Belgium have 2 sites of nuclear, Doel and Tihange. So the 15 EFIT is 6,000 megawatt thermal. Belgium, in 2 sites, they have 9,000 megawatt thermal. If I take the largest site in France, Gravelines, 17,118 megawatt thermal on that side. If I take the largest nuclear site in Europe, in Ukraine, 18,000. In North America, Bruce in Canada, 19,000 megawatt thermal. And if I take the largest of the world, this is in Japan, 24,000. So what we want to build is a tiny park of nuclear. So we can fit it in one place for all Europe. Okay, I'm finishing. The MIRA is present in the ESPRI as well as in the set plan, and this is a good thing for us. Why? Because it opens the door for us for the EIB loans, and we started actually the procedure for having that. And the second thing that the framework program was doing very well for us, you see the number of partnerships that we have, And these are the Europeans, industry, organization, research organization, and academia. And to tell the truth, many of those collaborators are there thanks to the Euratom Framework Program, and it was a sort of leverage to get them interested in the project, and now we signed with many of them bilateral agreements. So it was a trigger. So that's also the added value when sometimes we hear Roger coming defending in SNETP that, yeah, you know, the tiny money of Euratom is a trigger, it helps you, and that. I can tell you today, yes, it's true. He was not telling us a story because he's not capable to get more money for us in the European Commission. It helps to trigger people to get to you. When they get to you and they work with you and they see that there is interest for them, then thanks to that little European money, and I don't consider it little, but in comparison with the budgets you need, it has an effect. So this is our team. We are 150. We are growing to 230 by the end of this year. So those who want, they can join us. Go to our website. There are plenty of positions open. But to conclude, the question is, are we dreaming to industrialize PNT? And I say, what is life without dreams? We have to dream. The people that changed the world were dreamers. So if we are continuously just making the one who counts the cents and the euros, etc., you don't create hope, you don't create dream, you will not move, you will die. Second, Mira was a dream. Many people were thinking Hamid is crazy. Yes, I'm crazy, I'm a dreamer. But in a country that quit nuclears, it invests in a project of 1.6 billion euro of nuclear, but it's not called nuclear. Okay, but I think we have to join effort on this project, which is available to offer to our young people, talented people, needs challenge. And we offer it for that. And I think when we say we offer it, we are also welcoming participation, really becoming member of this. And we should now also do something that we didn't. As I said, unfortunately, we fissioned P from T in FP6. I personally think we have to do two things. Stefan, in his talk, he showed us how much P is important. He said, you are building machines, you are not building the roads. He's right. So we need to strengthen P and to do what we succeeded to do for the block 3. We need for block 1 an advanced partitioning, demonstration, lab scale, not lab scale, but pre-industrial scale. It should be our objective. And another thing I would love to do is that we make a concerted action on rejoining P and T in order to optimize and revisit our strategy that we established 20 years ago. Maybe there are things that have changed and we have to actualize it and to put it in the horizon in NI 2050 of NEA. We are in charge of this. I will be really loving that this concerted action happens. And to finish, this is a citation from myself. Ceci n'est pas un réacteur. And you can imagine to whom I refer. We are a country of surrealism. But Mira is not what I wrote, une œuvre scientifique. C'est une œuvre scientifique et technologique. Ce n'est pas une œuvre artistique. It's not an artistic work, it's technical and scientific work. But it got inspiration from artistic people. And so, ceci n'est pas un réacteur. Ceci n'est pas une pipe. Le pays du surréalisme, country leaving nuclear invest in a big project of nuclear. That can happen in Belgium. Thank you very much.
Is an outstanding speech, outstanding, let's say, case for PNT and for Mira technology. Are there any questions to Professor Ait Abderrahim? Yes, please.
So actually, I have a short question about, let's say, roadmap of Mira. When you will have, when will you have Mira?
The first part, so as I said, the accelerator up to 100 MeV and the proton target facility, we will have it in 2026. The second part means the prolongation of the accelerator plus the reactor. We foresee to obtain the construction permit in 26, and so we would start building it in 27 with the objective to finish it by 2033 normally. Unfortunately, we didn't succeed to convince other partners in the meantime. That would be done completely in one shot, but today we say we have to do it in this phased implementation approach.
Okay, thank you.
33 will be the reactor also there for starting the commissioning.
Other question?
Thank you, Hamid, for your very nice presentation. And I guess that you deserve also some compliments if a surrealistic country like Belgium is now financing this. Certainly you have played a big part on that, so compliments for this. I have two questions, a simple one this time. So if you can tell us a little bit more of what is this prototype facility, the PTF or something like that. And the second question is, you have put forward in a clear way that the partitioning is an important part for the full PNT picture. Mm-hmm. And you have also shown that ADS is much more efficient in burning minor actinides with respect to fast reactors. But ADS would need the uranium-free fuel. So also in the field of to achieve the 35 kilogram per terawatt hour, you have to go with inert matrix fuels.
No,
not necessarily.
The 35 kilo per megawatt hour.
Per terawatt.
Per terawatt, sorry. It was with a matrix which is made of a mix of uranium and dirty plutonium.
Ah, okay.
Yeah.
In the ADS.
Yes.
Okay.
So we put in there 40% of americium, and there are some tests that we put. We can add few of neptunium that we added, and curium. We were asked the question: shall we try to put curium? I said no. Curium, we leave it on the side. It will decay to plutonium, and that's it. And so I think because the fabrication of the fuel with curium will be a mess.
Sure.
But what concerns we looked if it would be interesting to make, a uranium-free target, so with metallic cermet of Cercer, etc. But to tell the truth, I believe there are two better matrices: the thorium oxide, and second, stick to just a mixture of uranium and plutonium, and their dirty plutonium is not a problem for us. The problem is, can we fabricate it?
Yeah.
But I think personally depends what you call dirty, how dirty you are.
Yeah, but also charging 40% of americium, I guess, would need some R&D still.
I think the R&D, there also what we need, to tell the truth, is beyond the R&D. R&D we conducted enough in Malab. We have to enhance Malab to be capable to handle more than 20 grams of americium per batch. We need, to tell the truth, if we would be dreaming, it is allowed to dream, following Hamid, 100 kilograms of minor actinide. Today, we are acting to go to 100 kilo of actinide without precising minor, etc. So I think this will be already a very good step. Okay. If we succeed to do that in Karlsruhe, fantastic.
Mm-hmm. Okay, we'll see. But tell us about this PTF a little bit.
Yeah, the PTF, I don't have a picture here, but I have in another presentation. But the PTF, the Proton Target Facility, is an extra building that we included close to the accelerator, which is actually hot cells and experimental hall, where we will have an isol facility. The isol facility will allow us to make physics, fundamental physics, but also production of alpha emitters radioisotope for medical application. We have a post-acceleration hall for the isol, and we have a classical chemical production facility. And also what we added in that PTF, but in a separated building, is a target for making fusion material irradiation. With the protons of 100 MeV, we can mimic in a certain way, but with small samples, aspects for material for fusion. And this is what PTF will do. But the first objective of that phase 1 is testing the reliability, you know, the intense reliability we have to achieve. That's also part of it.
Thank you, Amit. Thank you.